This video and the next are to get you ready for all of the spiraled level 1 continuity and differentiability problems spiraled for this week. So the first question is, for a function to be differentiable, what two things must exist? First, f of x from the left must equal f of x from the right. So ultimately, in picture form, if this was f of x from the left, call it f of xl, then it's got to match with f of x from the right. Often we say, hey, this is really f of x, and this is a different function, g of x, but that doesn't really work with piecewise functions. So we could also say f of x equals g of x, or you could even say, hey, y1 has to equal y2 if you were doing it on your calculator. The next thing that's important is that f prime of x from the left has to equal f prime of x from the right. You could also say f prime of x must equal g prime of x, or you could say derivatives must match. Here would be an example of a time where they do. The red might be f of x, the green might be g of x, and so you can see that the slopes match. Here's another problem where the slopes don't match. This m would be 0, and this m looks like it's about positive 1, slightly flatter than positive 1. And 0 does not equal 1. So that's a refresher on differentiability and the two things that you must have. Now we'll have an example where we've got a piecewise function. What are the points that you must check in order for something to be differentiable? Well, anytime they meet. So in this case, they'd have to meet at -1 when x is -1, and 2, and then 3, and then lastly at 4. If both the function f of x equal g of x and the derivative f prime of x equal g prime of x, if you satisfied those two conditions at each point, then you would have a completely differentiable piecewise function over the entire domain. So we'll go ahead and do that so that you make sure you're comfortable doing this in the future. Again, you can pause and jump ahead at any time. But in this first case, f of x would be -2 times whatever x is minus 1 from the left. And from the right, it would be whatever x is squared. When I plug -1 in, I get 1 on the left and 1 on the right. So we have continuity at x equals -1. Now we'll check to see if the slopes or the derivatives match. In the first one, we take the derivative of -2x minus 1 and we get -2 no matter what x is. On the right, you have 2x where the slope depends on the x. Plugging in -1, you get -2. And -2 equals -2, so we would say yes, differentiable. Now we'll look at 2. So we're looking at those two functions. Well, x squared now is equal to 4 when x is 2, and 4x minus 4 is also equal to 4. So we have a check there. Now let's check the derivatives. The derivative of x squared is 2x, which would equal 4 when x is 2. Similarly, the derivative of 4x minus 4 is 4. Our derivatives match. So we would say yes again. Now we'll look at 3. Here we have 4 times 3 minus 4 equaling 8. And when we plug in 3 in to negative 1 times 3 minus 4 all squared plus 9, we similarly get 8. So far we're looking good here too. We match the continuity side. Now let's look at the derivatives. The derivative of 4x minus 4 is 4. I'm going to do the derivative of this next one up here. We're taking the derivative of negative 1 x minus 4 squared plus 9. When we do that, we bring the 2 down, and we have 2 times negative 1 times x minus 4 to the first power plus 0, because the derivative of a constant 9 is 0. If we simplify this a little bit, we have negative 2 x minus 4. And when I plug in a 3 here, I have negative 2 times 3 minus 4. Well, that is positive 2. And you can see for the first time, the derivative from the left is 4, the derivative from the right is 2. So no, we are not differentiable at x equals 3. So on the entire domain, it doesn't pass differentiability because we have to be both continuous and the derivatives must match at each point. But we'll just check to see what it looks like at x equals 4. The y value equals 9 both sides, so that's a check. And the slopes equals 0 both sides, so this would also be differentiable because 9 equals 9 from the left and right, and the derivative 0 equals 0 from left and right. One thing to keep in mind, the problem on your last summative test and your final exam, instead of f of x, we were dealing with velocity. So velocity from the left, velocity from the right, and acceleration from the left, acceleration from the right, because acceleration is the first derivative of velocity. Now the last piece on our example problem, explain how this procedure is similar and different to a problem such as the following. Find constants a and b such that f is differentiable over its entire domain. So this is a very similar problem using differentiability and continuity. In the last problem, all we had to do was check to see if f of x equaled g of x and f prime of x equals g prime of x. A similarity is that we're going to use this same definition of differentiability, but in a slightly different way. In this new problem, we would let 3 minus x equal ax squared plus bx. That is satisfying the first part of the definition. Then we'd have to take the derivative to ax plus b. That would actually probably go over here. That must equal the derivative of 3 minus x, which is negative 1. In this problem, we would go ahead and plug in 1 for all of our x's. And we would have enough information, we'd have 2 equations and 2 unknowns, and we could solve for a and b. I would encourage you to solve this to make sure you can, because this kind of problem has been on tests and it'll be back around. B equals 5. A equals negative 3. So the similarities were use f of x equals g of x and f prime of x equals g prime of x. A difference would be solving to find a and b instead of just checking to make sure that both derivative and function were equal. Go ahead and pause this. I'm going to give you a couple example problems to work. So here's the answers. We are not differentiable because our derivatives don't match at -1, and we are not differentiable because the function f of x does not equal g of x at 3. Everywhere else, at all the other junctions, they are differentiable. You can watch this video as many times as you want. Now try the practice problems in your homework or your review sheet.